So, okay, so now we have the third talk. I know that we're a little off time, but we have time, by the way. Time is always is free, right? We have all the time in the world. We don't have to go anywhere. We have the next speaker, Stan Lipovetsky, being a contributor to the HB for a long, long time. And I know that you have done very interesting stuff in more mathematical than some other people. So you are welcome to start talking about your talk. I'm not going to say what the talk is about. Should I say what the talk is about? I suppose I should, right? Oh my, I can't even find my own screen. Where is my screen here? This one, no, that one. Priority vector estimation, consistency, compatibility, and precision.
Yes, thank you.
Stan, there you are.
Can you see my screen?
Yes, terrific.
In this work, I wanted to answer to such a general question: which solutions are better in any sense? So how to judge if we have several ways to estimate priority vectors, what makes more sense, what to apply, and on what it depends. And mostly in this work, these four techniques will be compared. They are called usually eigenproblem method, EM in short. It's classical analytic hierarchy process suggested by Thomas Sati. The next least squares method proposed in Sati and Vargas. Here you can see that work of 84. Also logarithmic least squares, also called multiplicative method, also Sati and Vargas, and proposed also by Lutzman. And technique called here robust estimation. It's less known. I was co-authors considered it, and robust in that sense that if we have some pair comparison which is not consistent with others or less consistent with others, which could be checked, and those can be identified by some techniques described in this papers at the bottom of the slide. This technique produce anyway almost the same solutions. It's less sensitive to possible deviations in some pairwise comparison, relatively others. Okay, so how to compare several solutions? Suppose we obtain those four solutions by those four techniques. Are they comparable at all? And what to apply for seeing by some simple index or measure, are they similar or not? First is, of course, regular pair correlations or cosines could be used. Mostly they produce the same results, so we can use one of them. The next mentioned today already is Sati compatibility index, S compatibility or S index, suggested already 15 years ago. And not very much used because it's not very much clear what actually it compares, on what it depends. The next, more recently suggested Garuti compatibility index, G compatibility. Also, it is maybe more explicitly clear what does mean, but again, both indexes S and G there are rather some heuristic measures of are two vectors close or not. They make sense, they're reasonable, but they are not derived in any way. But in practical needs, of course, they can be used, both of them. Garuti compatibility index is more sensitive, I would say, by various rounds, which I made. Also, of course, it makes sense to compare vectors when they are obtained for different sizes of items compared and different consistency of matrices or judgment, because those comparisons could depend on such setup, in which conditions we compare vectors. Just a moment. And also we need some other measures, I would say, of more statistical kind of estimations, which we also can describe. So to remind several positions of HP in which we can consider the further work. Pairwise comparison matrix, classical matrix, suggested for analytical hierarchy process by Thomas Sati. Theoretical matrix, which can be presented by some theoretical vector of priorities in outer product with reciprocal to its vector. From this, we can get theoretical relations with this matrix, and by it we can construct a relation which is eigenproblem for empirical Sati matrix or observed matrix of elicited data. Then we have the second method. Well, here in Formula 3, all of you know, we take eigenvector with maximum eigenvalue. It is classical eigenvector solution. Another way, least squares estimation. It is derivable. It corresponds actually to singular value decomposition for the matrix A. And also the first eigenvector, it is priority vector in least square solution. Multiplicative, formula number 5. Also, it is derivable. It is least squares of the values in the pairwise matrix of comparisons, but in logarithmic scale. So this solution also is derived. And we have usually normalization of all those solutions to total equals 1. Okay, here is less known, but published, so it's easier to find it. That robust estimation. Actually here from original theoretical priorities W, we can go to their shares U, which is a share of priority for the item I in two priorities of I and J items. So we can reconstruct Sati matrix to this new matrix of shares of priorities. And for this matrix, we have let's go to formula 12. If we have regular pairwise elicited value of the element of sati matrix A, I, J. So comparison between I and J items. The new value of shares of priorities would correspond to this value B at J, which is original A divided by 1 plus A at J. This transformation takes all the elements from 9 to 1 over 9 from original values to the span from minus 1 to 1. So matrix becomes symmetrical, or more exactly skew symmetrical, because transposed elements have different signs. Because now we don't have too much difference between, suppose 9, if one item is 9 times bigger or better, preferable than other, to 1 over 9. Those are less comparable than values within the range from minus 1 to 1. And in this sense, this technique becomes more robust to possible deviations in original elicited pairwise values. For this matrix with these elements in formula 12, we have such kind of eigenvalue. Instead of classical analytical solution, now we have eigenproblem number given in the formula 13. So essentially it's very easily solvable, so no problem with this. Then classical measures like consistency index and consistency ratio, they are useful measures. Without them, we indeed don't know. Does it make sense to consider those vectors for some kind of making sense estimations? So let's go to comparison of the vectors. Here is formula 16. It is a regular pairwise correlation without last items 1 over n, it will be cosines. So essentially they are very similar and by numerical values too. Here we have, in 17, we have S index. So Sati suggested measure of compatibility. And the next formula is Garuti G index, suggested in his works. Both Sati and Garuti indexes, the closer they are to 1, the better. They go to 1 from different sides. So Sati from upper side to 1, the better. Garuti from the lower side to 1, the better. And here, what I found is very useful. It's besides those measures of are the vectors close or not, to compare vectors with the matrix itself by which it is constructed. So it is a regular statistical measure, like in formula 19, what we have standard error. What is it? When we estimated alpha, like priorities from any eigenvector solution. Let's go back to matrix A, J, K, find deviations of each pair comparison already from vector to the original elicited pairwise comparisons, and find the standard error measure to compare different solutions how they reproduce the original matrix. Another very widely known and used in statistics, mean absolute error in Formula 20. Similar kind, but deviations by absolute value. And from them we can consider even more convenient measures like multiple determination coefficient known in any regression statistical modeling. Here we have in numerator on the right hand side. It is the same standard error divided by something similar to standard error relatively to some mean level. When all theoretical priorities are the same, so ratio of them is 1. It's very convenient measure, this R squared. It is usually from 0 to 1. Usually, I mean, when solution makes sense. If we have some out of normal meaning solutions, then that R square can be on not in this range. Anyway, this formula can be easily generalized to many respondents, and it was made in one work. So I have not much time, so several examples. Here is classical society example, choosing the best home, described in society Varga society. For this matrix, what we have, here are those 4 solutions: eigen vector methods, least squares, logarithmic, and robust estimation. They're very similar, so difficult to tell what's better. Correlations between these vectors are very similar, very high. As compatibility, mostly they are compatible if deviation from 1 is less than 10%. So we shouldn't consider diagonal, but all the others. Diagonal is comparison with itself, so it's totally compatible, of course. G compatibility between these 4 vectors. Also, we can find some small better or worse features, but essentially it's the same, both indexes. Precision, here we can find what is better. For instance, by standard error, when it is less, it's better. Or mean absolute error. The best here is the last technique. The next is logarithmical. The next is eigen method. The worst least squares. What does mean these units? It is mean deviation from elicited values. So we can be wrong by 1 unit in those which are above 1. R square. By R square, so relatively to the case when all priorities are the same. Logarithmic method is the best here. But it is for the matrix of not totally best features. Look at here, for instance, consistency ratio. It is too big. As we know, it should be somewhere closer to 10% or less. So if you go to another example, for instance, this also classical. So it's example distance from Philadelphia. And here are several cities in different countries and continents. Here, consistency index is very good in ratio. here is very good estimation of those distances. So here we have those 4 solutions and actual distances because they are known, and correlations between them. So we can judge what is closer to actual distances, for instance. Here, eigenmethod is the best, then logarithmical. S compatibility, well, all of them are good. G compatibility. Eigenmethod is good because it's less than 10% deviation from 1. Least squares is not good. Logarithmical, better. Robust, not good. So by precision, amazingly, we have the biggest deviation, for instance, by standard error or by mean absolute error. Biggest deviation is from actual distance data. So what we can conclude, that estimations themselves, also they produce very good consistency index, but estimations were not so good. Here we can judge by this a posteriori statistical evaluations that what was elicited from experts is farther from actual data than estimations of eigenvectors to elicited data, but not to the actual distances. So R square, for instance, is the worst for actual distances. So the data itself is not very good in spite of good consistency index and ratio.
Stan, you have to wrap it up because we're going to run the next session in a few minutes.
Well, here is another example with slightly different results. And as conclusions, I can say that we should develop more statistical measures for evaluations and matrices elicited from experts and of their estimations for priority vectors.
Okay.
Well,
they're going to disconnect.
I simply want to refer to previous work, but for now, that's all. Thank you.
Thank you, Stan. They're going to disconnect. It's going to run to the next session, which is at 1:05. I'm so sorry about that. So thank you very much to all of you for attending, and I'll see you tomorrow, maybe later.
Yes, thank you.
Margarita, you take charge. Elena.
Thank you.